Imagine a humanoid robot walking through a cluttered room, picking up a cup, opening a door, and placing the cup on a table, all in one fluid motion. No jerks, no stumbles, no unnatural wobbling. Just smooth, human-like movement, composed of coordinated steps, precise grasps, and seamless transitions between actions. This isn't science fiction. It's the future of humanoid control, and it's being built with a new framework called MetaWorld-X. At its core, MetaWorld-X tackles one of the hardest problems in robotics. How do you teach a high degree of freedom humanoid to perform complex, multi-stage tasks like locomotion and manipulation at the same time, while moving naturally, staying stable, and generalizing to new scenarios? Traditional reinforcement learning methods try to solve this with a single monolithic policy, a one-size-fits-all brain. But that leads to a fundamental problem: skill interference. When the robot learns to walk and reach and carry, the neural network struggles to balance these conflicting goals. The result? Jittery motions, unstable postures, and unnatural gaits. It's like trying to juggle 3 different sports at once. Your brain gets overwhelmed. MetaWorld-X solves this by taking a divide-and-conquer approach. Instead of one giant policy, it uses a hierarchical world model with 2 key components: a specialized expert policy module and an intelligent routing mechanism powered by a vision language model. Let's break this down. First, specialized expert policies. Each expert is trained on a single fundamental motor skill, like walking, running, sitting, reaching, or carrying. But here's the twist: these experts aren't just trained to succeed at a task. They're trained to mimic human motion. How? By using motion captured data from the AMASS dataset, real human movements recorded in 3D. MetaWorld-X then uses a motion retargeting pipeline to map those human motions onto the robot's body, aligning joint angles, velocities, and trajectories. But even with perfect motion data, the robot can't just copy it. There are differences in body shape, dynamics, and control. So MetaWorld-X introduces an energy-based imitation reward that measures how closely the robot's motion matches the human reference, not just at a single point in time, but across the entire trajectory. This reward is exponential. It penalizes large deviations, but also ensures stable gradients even when the robot is far from the target. The result? A policy that learns not just what to do, but how to do it, like a human. And crucially, because each expert is trained in isolation, there's no cross-skill interference. Walking doesn't mess up reaching. Reaching doesn't destabilize balance. The system is modular by design. But now comes the real challenge. How do you combine these experts into a coherent, complex behavior? That's where the intelligent routing mechanism comes in. Imagine giving the robot a high-level instruction. Walk to the door, open it, go through, then pick up the cup and place it on the table. You don't want it to just randomly pick experts. You want it to understand the task, sequence the actions, and switch smoothly between them. MetaWorld-X uses a vision language model, like GPT-4o, as a supervisor. The VLM interprets the task description and generates semantic guidance. This task involves walking, then reaching, then opening a door. This semantic signal is used to train a learnable routing network, a lightweight neural module that dynamically assigns weights to each expert based on the current situation. It's like having a conductor in an orchestra, deciding when to bring in the violin, when to shift to the cello, and when to let the whole ensemble play together. But here's the clever part: the router doesn't need thousands of examples. It uses few-shot semantic transfer. Just a few demonstrations are enough to teach it how experts should be composed over time. The VLM provides coarse task-level guidance. You should use walking and reaching, while the demonstrations refine the timing and sequence: first walk, then reach, then open. This creates a hierarchical semantic distillation pipeline. At first, the router is heavily guided by the VLM. As training progresses, it shifts toward learning from the demonstrations, eventually becoming autonomous. And because the routing happens in real time during inference, there's no need to query the VLM every step. The router is fast, low latency, and ready for high-frequency control. Now let's talk about results. On the humanoid benchmark, consider the gold standard for humanoid control. MetaWorld-X outperforms strong baselines like TD-MPC2, Dreamer V3, PPO, and SAC. In locomotion tasks like walking, running, and standing, MetaWorld-X achieves significantly higher returns, faster convergence, and superior motion quality. It's not just better, it's more natural. Watch the gait: smooth, balanced, with coordinated arm swings and stable head posture. No robotic stiffness. In complex manipulation tasks, like pushing a box, carrying a package, opening a door, or playing basketball, MetaWorld-X doesn't just succeed. It generalizes. It learns from a few demonstrations and applies those patterns to new variations of the same task. For example, in the door opening task, the router learns to switch from stand to walk to reach at precise moments: 0, 17 million steps, then 0.74 million, then 2 million. That's not random. That's semantic-aware planning. And when we ablate the system, removing the VLM, removing imitation learning, removing the router, we see the full picture. Each component is essential. Without the VLM, the robot fails completely. Without imitation learning, it never converges. Without the router, it learns slower, even if it eventually works. This proves that semantic grounding is not a luxury. It's a necessity for compositional generalization in robotics. So what's the big picture? MetaWorld-X isn't just another reinforcement learning algorithm. It's a paradigm shift. It shows that predictive modeling alone isn't enough. Imitation alone isn't enough. But when you combine human motion priors, world models, and semantic-driven expert orchestration, you get something greater. A system that learns natural, stable, and generalizable behavior, just like a human. And this isn't just for simulation. The architecture is designed for real-world deployment. The lightweight router, the efficient world model, the modular experts, they all scale. Future work. We're exploring tighter integration between semantic reasoning and dynamics modeling, expanding the expert library to hundreds of skills, and testing on physical robots. Because the goal isn't just to build smarter robots. It's to build robots that move like humans, naturally, gracefully, and with purpose. If you're interested in the technical details, how the energy-based alignment reward works, how the routing network is trained, or how motion retargeting handles joint limits, check out the full paper and code at SIT 2004, GitHub, eo/MetaWorld-X. This is the future of humanoid control. And it's just getting started.